we'll do some more of chapter 5. I've got to make sure that I stop early because I've got your essay exams to hand back. That's not the right version. Okay. All right, so I was a little slow on Monday. We didn't quite get the last couple of slides done on that first bit. So I think we had got this far. I'm going to skip through some of this because we're still mainly talking about AMP, and so this should be reviewed for you. All right, so I'm going to go a little quick. Give me a yell if you're not understanding something. So we had this overview of the layout of the nervous system, bless you, okay? And we've got two main divisions, the central nervous system and the peripheral nervous system. The central nervous system is the brain and the spinal column. And then once the nerves leave the spinal column, everything else is peripheral, okay? So looking at the areas of the brain, the thing that I want to point out here, because it plays a role in how quickly we're able to respond to sensory information. All right. So when you look at the central sulcus here, right, just in front of the central sulcus is the motor cortex, and right behind the central sulcus is the sensory cortex. So they lie right next door to each other within the brain. So that's one of the reasons, that's part of the reason why we're able to respond so quickly to sensory information, is that information doesn't have very far to travel actually in the brain. If the motor cortex was over here or the sensory cortex was somewhere else, and that information had to talk back and forwards across the surface of the brain, our responses would be much slower. Right? So, and then spinal column, the diagram that they give you in the book is just showing the motor nerves. All right, so these are all motor neurons that come out of the spine, areas of motor coordination and control. Okay. And we're going to look a little bit at some reflex actions. Reflexes, remember, are an involuntary response to a stimulus, and they occur at the spinal column. They don't have to go all the way up to the brain. So the information coming into the spinal column can loop around within the spinal column, and we see a motor response to that stimulus without the information having to go up to the brain. Doesn't mean the information doesn't go to the brain, because it will also synapse with a nerve that's going up the column to the brain, so the brain gets that info. But the motor response, the reflex, is not a signal from the motor cortex. Right? It's just organized at the spinal level. So if I put my hand on a hot plate, my pulling my hand off the hot plate doesn't have to wait for that signal to get all the way up to the motor cortex. Right? So it acts as a safety mechanism. Reflexes are also, the more we're finding out about them, the more we're looking at how important they become in sport. So in sports like cricket and baseball, where you have to respond very, very quickly to a ridiculous ball. What we're finding now is that a lot of that response to a ball can be organized at the spinal level. So when you look at someone who's super experienced and highly skilled at hitting a very fast ball, a lot of that movement is being organized at the spine rather than coming from the brain. So part of the learning curve that we see appears to be developing a reflex to the ball rather than having to think about what it is that I'm doing to the ball. So, a basic reflex that it's easy to elicit in an adult, knee tap, right? Those of you that are taking athletic training classes, there's a little box on page, I think it's 120, that talks about how you can grade the response to a knee tap. So there are different levels of how big is the response that an individual shows to the knee tap, and they give you that information in the book, right? But when we do a knee tap and you tap the patellar tendon, then it stretches the quad, right? And so the muscle spindle sends a quick signal off to the spinal column, and that synapses with the motor nerve that then causes the muscle to contract. So remember we said that if we stretch the muscle quickly, the spindle is responsible for initiating a counter contraction to rescue the muscle. Right? The Golgi tendon organ recognizes force and would initiate a relaxation in the muscle. So one type of reflex that we see, one version of the reflexes, is something called reciprocal innovation. And reciprocal innovation appears as though it might be somewhat trainable. So we see an improved reflex with training, such as catching a ball or hitting a ball. So when you're looking at a reciprocal innovation scenario, what's happening is the signal comes up the afferent nerve, right, into the spinal column, and the sensory nerve then synapses with two different interneurons. One of the interneurons is called the facilitator interneuron, and that will go back to the muscle. The interneuron will then connect to the motor nerve, and the motor nerve will tell the muscle to relax or contract, depending on which sensory organ sent the signal. And the other interneuron that it synapses with is called an inhibitor interneuron. And so what that one does, that one then synapses with the motor nerve that goes to the antagonist muscle. So that allows for very fine control of the motor skill. I can organize the muscle that's doing the work, but I don't want any counter forces occurring that would take force away from what I'm trying to apply to the ball, say. So the inhibitor interneuron synapses with the motor nerve to the muscle the other side of the joint so that it isn't contracting and causing less force to occur. Does that make sense? So I don't want to contract my bicep and my tricep at the same time, maybe. depends on the skill. So reciprocal innovation, the research is showing, seems to be supported when we do lots of training. So it seems to work a little more efficiently. So we do see some training adaptation within the nervous system, although it's not, we don't see massive changes in size or shape or anything like that. It's a little more subtle than that. All right, so our peripheral nervous system is all the other nerves, glial cells, everything else that we have going on outside of the brain and the spinal column, right? And it allows the central nervous system to talk to all the other organs and tissues in the body, right? So the peripheral nervous system is subdivided into two sections, the autonomic and the sensory somatic. So our autonomic nervous system is responsible for organizing and controlling things that are unconscious. Okay? So your heart rate, right? You don't control your heart rate. It beats at the speed it beats at, and it's controlled subconsciously by the autonomic nervous system. Right? Blood pressure, digestion, breathing. You can override breathing and make it conscious. Right? If you think about it, if you fall into a swimming pool, you can hold your breath for a while, right? Not permanently. You can override the autonomic nervous system control of breathing for a little while. But for most of these functions, we don't have any voluntary control over what's going on. And we have another subdivision of the autonomic nervous system. So go back, right? I would recommend, this is what I would have to do if I was trying to read this stuff and picture it out in my head, is print this out and have it at the side as I'm working through these subdivisions. So you've got a visual cue to follow as well. All right? So here's our peripheral, right? We have an autonomic and a sensory somatic, and then our autonomic is divided into sympathetic and parasympathetic. Our sympathetic nervous system is the one that we call the fight or flight system. It's the one that's responsible for getting us ready, right? Either I'm going to stand there and punch the tiger on the nose, or I'm going to turn and run like heck and try and climb a tree before he gets me, right? One or the other. But to do either of those things, lots of stuff has to happen physiologically to be anywhere close to being ready. Right? So it responds to stress, whether that stress is emotional stress, whether it is physiological stress, right? Your body just recognizes stress, so we see an increased heart rate if I run. But if you have an argument with someone who's important to you, you also see an increase in heart rate. Right? So stress doesn't have to be a particular type for this system to kick in. So heart rate, blood pressure go up. Right? We see more blood flow to the skeletal muscles. Well, what is the blood then carrying to the skeletal muscle? What's in the bloodstream that we might want to use? Oxygen, right? So if I'm going to run from this tiger, I'd better have some oxygen available to make ATP so that I can run, right? Because he's probably not going to get tired. So I might have to run for a few minutes to get out of his way. Okay. Release of glucose by the liver. So liver is our backup glycogen storage. Okay. And if I'm going to need lots of ATP, I'm going to need lots of carbohydrate to make that ATP quickly. So when we're stressed, we also start to break down glycogen in the liver and dump it into the bloodstream so that the muscles can pick it up and make ATP. Okay. And we see faster breakdown of the stored glycogen within the muscle tissue to also provide more carbohydrate for energy. So that could be, as I say, it could be an argument, it could be jumping out of an aeroplane, it could just be running on the treadmill. Right? All of these things count as stressors that would stimulate the system to one degree or another. The bigger the stressor, the bigger the response from the system. Right? Acute stress to a point, exercise, is considered a positive stressor. Right? Chronic stress, so if I'm in a job I really hate and every single day I hate going to work and every single day I have a fight with my boss and every single day I'm sitting there depressed that I'm there, day after day after day, chronic sympathetic nervous system stimulation is a very negative response in the body, right? Some really bad things can start to occur when you see chronic stress in an individual. So, chronically increased heart rate, chronically increased blood pressure, okay? Chronically high blood glucose levels, all right? So ongoing stress is not a good thing, but exercise is considered a healthy stressor because it's short-term, typically. Right? When you look at people who do these 24-hour marathons and things like that, then they're starting to see some pretty bad levels of response. People who try to run marathons more often and don't take a long enough rest period would be causing too much stress on the body. Overtraining is a stress response to too much training without enough rest built into the training program. Okay? Does that make sense? Okay, the other half then is the parasympathetic nervous system. And this is the section of the nervous system that's responsible for calming us back down, bringing us back to normal, bringing us back to status quo, helping us digest our food, all right? Because when I do this one, all this blood flow to the skeletal muscles means I'm diverting the blood flow from doing other jobs. That means I'm not digesting food. It's one of the reasons why you don't want to eat a big meal and then go train. Right? Because when you start training, blood flow starts going to the muscles where you need it, and the food sits there in your stomach undigested. Right? Not comfortable. So my rest and digest system is going to help us maintain. So right now, your parasympathetic nervous system is predominant, right? It is in charge of what's going on in your body because you're sitting here chilled out. Right? If you just had lunch or you're eating lunch. Right? Resting function is controlled by the parasympathetic nervous system. So when the parasympathetic nervous system is switched on, then we see lower heart rates. It starts to bring the heart rate back down. It brings blood pressure back down. It increases the blood flow back to your skin and your stomach and your other organs. Right? Peristalsis, so the digestive contraction and relaxation of your digestive system resumes properly. Normal bladder function will resume, so one of the things you like if you run a lot and you run for a long time, right? If you get on the bike or you go for a run for an hour, how often do you have to stop and go for a pee? Right? And yet, how many of us can get through a whole class period and not need to go pee? Right? If we're drinking enough, a 50-minute, it's time to go for, but I can go for a 50-minute run and not need to go for a pee because we decrease bladder function in order to move that blood to the muscle tissue. So, lots of just maintaining resting function. Okay, brings your breathing back down. Okay, so the autonomic system is controlling all these subconscious functions that maintain the body. And the sensory somatic nervous system organizes the response to the external environment. So this is our sensory nerves and our motor nerves. Right? My sensory nerves are going to transmit information from whichever organ they're related to, so from my eyes, from my ears, from some kind of a skin receptor, pressure receptor, right? Golgi tendon organs, muscle spindles, and my motor division is going to carry the signal back to the muscle to contract in response to that sensory information. So autonomic does heart, breathing, digestion, and sensory somatic does responding. All right? Make sense? Are we still reviewing? Everybody remembering this? Okay. All right. So one of the things when we're working in teaching motor skills or training motor skills, and we're working out, we're exercising, we're getting people physically active, one of the things we want to be able to understand is how does fatigue happen, right? What is it that is making someone fatigued? Fatigue means decreased power output, not, oh, I'm knackered today, right? Fatigue, physiological fatigue, is measured by a decrease in power output, force output. Okay? So, within the central nervous system then, because we talked a little bit about, and we'll come back to it some more, we talked a little bit about when we're looking at the energy systems, if I don't have any more ATP or phosphocreatine left in my cell, I can't maintain that high power output. I have to slow down, right? If I run out of carbohydrate, I can't maintain glycolysis. It's very, very hard to run out of all food substances, so I can't maintain aerobic work. So we don't see a lot of fatigue when we're looking at aerobic work. We've got to go for quite a long time before we see fatigue in an aerobic event. So now when we look at the nervous system, where can we possibly see fatigue occur? So we can split it up depending on whether we're looking at the central nervous system or the peripheral nervous system. So the central nervous system could be involved. One of the things that's interesting is willpower, right? my psyche, my desire to keep pushing. Okay. So one of the hypotheses is that central fatigue could come from maybe a lack of attention. Right? I'm getting bored, or I'm demotivated, and so that impacts the motor output. How many motor neurons do I turn on? If I turn on less motor neurons, then I get less force output at the muscle. Okay. So one of the things you see with people who are really psyched to train, or who are really motivated, or are really excellent athletes, is this ability to overcome feeling tired, or to just keep pushing when everybody else is giving up, right? Even though their legs ache, their arms ache, they can still produce enough power to keep going, because they just absolutely want it more than anything else. The other form of fatigue that we see is in the peripheral nervous system. So, and here what we're looking at is what's going on once we're down at the neuromuscular junction and at the cellular level in the muscle tissue. Right? So, peripheral fatigue could be a lack of neurotransmitter. So the muscle at the neuromuscular junction, that would be our ACH, our acetylcholine. So if I run out of acetylcholine, right, or all the receptor sites are full, and so I can't attach any more acetylcholine to continue the action potential across the muscle. So is the fatigue occurring at the neuromuscular junction? Is it occurring as the action potential moves across the muscle fiber and down the T-tubule? Is it occurring at the sarcoplasmic reticulum? What if our calcium levels are low? Okay. Is it occurring at the actin-myosin interaction? So what's happening at the cross-bridge formation? Maybe we don't have enough of a particular enzyme available to move ATP to the myosin head. Right? So this is nothing, I don't have control over this. So with all the will in the world, you may still see decreased power output because of something going on in the peripheral nervous system that you don't have control over. Okay? Does that make sense? All right, questions on that? How are we doing? Does everybody eat lunch? Glucose flooding your brain tissue and helping you pay attention?
Would there be a way to manipulate your body to prevent fatigue?
The peripheral fatigue, one of the few training adaptations that you see in the nervous system is the ability to delay fatigue within the system for many reasons. So training helps you mitigate that peripheral fatigue as your body gets. I think if you don't provide enough calcium, the problem is you have a calcium store. So logically, to me, that makes sense. If I don't provide enough calcium, then my calcium levels could be low in my muscles. I think that's possible, but also then your body is going to start leaching calcium from your bones. Because I think if it had to make a choice, muscle contraction would be the priority over bone density. Because muscle contraction is going to save your life, and bone density isn't.
As humans, we don't necessarily need a calcium source, do we? As we do. So cows and or basic cow milk is okay.
You can get calcium from regular milk, soy milk. A lot of the fake milks add calcium to them to try to improve calcium content. Salmon is a great source of calcium. Yeah, it's important to keep your calcium content up, especially for the girls, but also for the guys. Very important. Okay, so we're going to start looking at this. We'll come back to this diagram quite a lot over the next few slides, because this diagram is responsible for what we saw when we looked at the cross-section of the muscle fiber, right? So when we have that cross-section, remember we said that a muscle is not type 1 or type 2, right? Muscle fibers are type 1 or type 2. So, when I take a cross-section of a muscle, and I can see all these muscle fibers in the muscle, right? Some of these muscle fibers are type 1. Okay? And some of these muscle fibers are type 2. And then some of them are going to be type 2As, some of them are going to be type 2Xs. So a muscle is not fast or slow. A muscle fiber is fast or slow. And it's the ratio of fast and slow fibers that make you fast or slow as a person. Does that make sense? Okay? That's important, because this is dictated by this. Right? So, a motor unit, the term motor unit stands for the motor neuron, the motor nerve, and all the muscle fibers that that motor nerve synapses with. Okay? The motor unit is the nerve plus the fibers that that nerve attaches to. So unit 1 on this diagram, these muscle fibers are part of unit 1. Motor nerve number 2 is synapsing, and they synapse with hundreds, up to 100, can be hundreds of muscle fibers. Right? So it depends on which type of motor nerve it is. So, let's say, for argument's sake, right now, motor neuron number 1 is type 1. Right? And motor neuron number 2 is a type 2. And we won't decide whether it's a X or an A. We'll just say it's a type 2. Because all these fibers are attaching to the same motor nerve, they are all type 1 fibers. So a motor unit can only be type 1 or type 2. Motor unit is a motor nerve and all the muscle fibers that motor nerve attaches to, synapses with. So, all the muscle fibers that attach to one motor nerve within one unit are of the same type. This nerve doesn't attach to some type 1s and some type 2s. So everything that synapses with this nerve is going to be a type 1. Everything that synapses with this nerve is going to be type 2. It's an important concept because when I train and when I create movement skills, my brain has to decide which nerve am I going to turn on. Not which muscle am I going to turn on, which nerve am I going to turn on, and therefore which ones of these fibers within this muscle am I going to contract. So that's one of the ways the brain controls how much power this muscle can. Think about it. What can I do with the same muscle? Okay? So if I'm walking on a very thin sheet of ice, which type of muscle fibers am I turning on? I'm going slow, I'm going careful, I'm turning on type 1s. Now what am I doing?
Okay.
Type 2. Did I use the same muscle group? Okay. Same muscle, two totally different actions. Right? Same muscle, different actions, because it depends which fibers I turn on, which motor unit do I turn on, how many motor units do I turn on, because we always draw these diagrams really simplified, right? But there's never only 3 muscle fibers attached to a motor nerve. That doesn't happen. And there's never only 2 motor nerves synapsing with a muscle. That doesn't happen. Right? So think about that, because we're going to come back to that on Friday and develop that further. Okay? Because it plays a big role in what we do and what we see happen when we train. Okay, I have your essay exams.
She was trying to wake the nigga up.
Because I'm learning how to use Blackboard and the software in Blackboard, and on this particular occasion it decided not to work, I haven't got this into Blackboard yet. That means that you don't have the rubric right now, you've just got the bottom score on here. What I will do, hopefully this afternoon, is go into the rubric on Blackboard and give you the points for each element so that you can see how this score was created. Okay?